Okay, I think I'm making your friends work. Thank you for others who worked to have all these numbers. Now, number one, observation. You are also hearing me, I suppose. Now, look at the runs. This is the fake part. Okay, runs are usually 3. There is 1, 5. Okay, and the other is 2. There is 1, 2. Whereas here, the runs are, you have a lot of 6s and 7s. Okay, because it is really random. Random means that you are getting the extreme cases as well. Okay, that's the meaning of random. Okay, random is not only made up of the average. You are getting the extremes. This is extremely important. Okay, so it means that as a human you cannot fake numbers. Let me tell you a story about this. Okay, can I have your attention, please? Full attention. Now, there has been a research done in a field, which I'm not going to tell its name, but a researcher, in a very renowned institution, faked some numbers in the hope that it will fit the objective of the research which is carried out without actually doing the experiments. I'm talking about real physical experiments. But instead of that, randomly, not even generated, because he wanted certain results to be true and put numbers accordingly. So this is basically how that person was caught. Was very simple. Okay? They did some statistical tests on the numbers, found out that those numbers were very perfect. For statistically speaking, you shouldn't have those perfect numbers, actually. And that was the way that it was understood. And then he confessed. Teşekkür ederim. Okay, so this is number one. They did a similar analysis partially to the results of elections in Turkey to find out whether there were consistent, okay, changes in numbers compared to previous years. Consistent means that, or no, excuse me, inconsistent changes with respect to previous years. And in the small sample that was analyzed, they couldn't find any. So the idea of being, well, there are different rumors going on. So one way to test it using statistics, actually. So statistics in that respect is a powerful science, but you have to know how to use it properly. Now, so this means that if you are doing a project, you should never fake middle group. You shouldn't do that. Okay? This time I'm not going to do anything to you, but next time I will not allow that. Okay? Well, don't look at me like that. Okay. I'm not going to do anything. These are the good students, the bad students. Okay. Now, let's look at the numbers. Now, what I will do is I will analyze the numbers in a little bit different way. So you should please help me in bringing up these numbers together. So count, let's look at t's. How many 7s are there? There is, the smallest number is 7, am I right? Okay, how many 7s are there? 2. So let me do it this way. So this is, let's say, 2. Okay? So this is 2 7s. How many 8s are there? Count and tell me. And somebody please count 9. Somebody count 10. Somebody count 12. I think you have all the numbers up to 12. So 8. What is, how many 8s? 3 8s. Okay, so let me write 3. How many 9s? 3. Okay, how many 10s? 9. Okay, how many 11s? Okay, 4 or 5? 5. How many 12? 2. Okay, so this is the picture. So you can see that the spread that was obtained by this group is in between 7 and 12. There is 113, I'm sorry. I didn't see that. Who is that group? 13. Okay, good, yeah. You're playing devil's advocate. Okay, which is good. So you can compute the average, but you can see that it will be a number close to 10. Okay, more or less. But the spread is only in between 7 and 13. I already talked about the runs. Now let's do the same thing here for the real one. Okay. Now here you can see that the number of t's can be, smallest is 5. And what is the largest? There is 15. So from 5 to 15, this was something that I wrote before we had those numbers there. Okay, because there is some kind of a scientific way of analyzing these results. There is a certain distribution that you obtain, and more likely the range is going to be in between 5 and 15. I don't have any theoretical information on the biases that this middle part of this classroom is creating to the class. Okay, I have no information on you personally. Okay, so I'm not going to do that, but you can see that the spread of the real numbers is much better. Now, question here is, what is the relation? Now, any questions on our findings? Now, you're going to do this more formally in some other courses. Okay? I am simply trying to get your attention, and I hope I got your attention, because you basically are involved in creating the numbers. I didn't do any games. I would usually do, but there is only one thing that I told you that may have affected you. Without me saying it, probably you already knew that. And I told the middle group while I was walking around that, of course you know that you are expected to have equal number of t's and h's. Okay? That's what I told while walking, not to everybody, but implicitly. So I simply reminded you that you should be biased. Okay? That was my reminder. And some of you, actually, in their writing, they said we have 10 heads and 10 tails. So you were very proud of having that as a result. Okay, which is good. Okay. Okay, so I created some bias in this classroom. But other than that, this is usually what you will get. And this is actually important. Any questions on this? Now, I'm going to relate this to our barbershop examples. Okay. Now, so let's keep it there, and let me move with some more specifications of queuing systems. Okay. Okay. Op. Ay. Okay. I'm sorry about that, yeah. Did anybody took the note of that? Well, we have it in the camera. Okay, you have to look at the course videos. Okay. Now, what I will do now is I will give you some jargon on the queuing systems. Now, we have to agree on this jargon so that I will not change the jargon every time that I change the example. Okay, the jargon is very simple. I am going to have the queuing system, which is going to be made up of server or servers. So I'm going to show it with a box. It can be a single barber, or it can be a couple of barbers in the same shop. It can be the telephone, the service provider who is working in somewhere in Gümüşhane, okay, answering your phone calls, or in India if it is in English. Okay? So they are basically working there. So the group of people sitting, there is one service provider, service center of Turkcell, for example. So we're talking about all the operators of Turkcell answering your calls. So this is the server system. And we as customers are here, and I'm going to show it in this manner. So customers arrive at the system, and here we have servers. Customers get service, and here they exit the system. So whether the system is a barber shop, whether the system is a call center, whether the system is a cafeteria, this is going to be the jargon that I'm going to use. We're going to have customers, we're going to have servers, and we're going to let the customers exit the system once they are served. Now, there are many possibilities with respect to how the servers are going to handle the customers. Now, one thing that can be done is FCFS, which is first come, first serve. So this is actually how things are done in front of ATMs. ATMs they don't differentiate the customers. You simply wait in the line and wait until you are served. Or in some cases you might have some priorities which will determine how and when you are going to be accepted to the servers. Okay? Now, of course, you're going to see these in detail in 325 and in another course. Okay? So it is basically a topic one of the topics that you're going to see. But you can see that there are many different ways that the customers can be accepted. Let me give another example. Last in, first out is another priority possibility. What do we mean by that? You're last to arrive, but you're served first. Is it possible? Have you seen this happening? Okay, very simple. Let's say that I am giving a D-lecture. Okay? So my D-lectures are going to be collected, and they are going to put one by one at the top of each other. Then at some point in time, I will come to my desk and start processing the D-lectures. Okay? This is last come, first served. Okay? Very natural, actually. So this is not something which we would like to have. It's not fair. Okay? Fairness is very important in queuing systems. That's the reason why all elderly people especially get very angry when somebody joins the queue. We call it welding, kaynak. Okay? Okay, we simply join the queue saying, hi, how are you, to a person that we have never seen before, just to be able to go to the front and like we will be as sympathetic as possible. How are you? Smile, laugh, and so on. But it doesn't work when I am there. I will say, go out. Okay, I'm very strict in this. But this is actually one thing that we really want to have. We want to have fair lines. So first come, first serve in that respect is fair. But if you ask me, if you are doing some kind of a business, priorities are also fair up to a certain extent. Okay, anyway, but this is basically called serving discipline. So serving discipline means that server takes next customer from the waiting line as on the basis of first come, first serve, or on the basis of last come, first out, or on the basis of some kind of a priority. But it's called the discipline. Now, if the server doesn't have any discipline, what does that mean? Everybody will be equal, and I will call one of you randomly. Okay, so you will be waiting there in the hall, and I will say, whoa, you come. Okay, that's also called random discipline. So it's also a discipline, actually. Okay, so this is actually a discipline. Now, another jargon that we use is we say that customers arrive at the system. So arrival means that a customer is coming to the system. So we're going to call it arrival. So each time that a customer arrives, we're going to call it an arrival. Okay, so it will be arrival. Now, in the simple queuing systems, we're going to assume that customers arrive one by one. Now, so you're not going to have your buddy friend coming into the line exactly at the same time, because we are assuming that there might be a second difference in your coming, which is it's a reality. If you think about the time continuously, one of you is going to be in front of the other. You cannot move exactly in the same way. Okay? So we are assuming that the arrivals will be one by one, and you might not be able to see unless you get an elective course in more complex arrivals. Okay? You might not be able to see that. Okay. Now, of course, it is important that the whole thing is called a system. So when we say the average or the expected waiting time of a customer in the system, we mean actually the total time that the customer is going to spend from the time of arrival to the time of exit. And if we take the average of all of them, we're going to call it the expected waiting time of a customer in the system. Now, similarly, we might have the same thing for the queue. So we might actually analyze this part separately. So the first person in the queue means that that person is the first person to be served when server is available. Okay? But we can do the same thing for the server. So the expected waiting time of a customer in the queue is another performance measure that we consider. So time is important for us. Okay? That's the reason why we consider this as a performance measure. Now, a related performance measure will be the expected number of customers in the system. So not time, but the number of customers in the system or in the queue will be other performance measures. Because basically when we look at, for example, when you enter the bank, you simply count the number of people who are there. Okay? And then you say, well, on the average, it will take 5 minutes. So if I wait for 15 minutes, things will be resolved. Okay? So this is actually another, so we have 4 performance measures that we are going to use for queuing systems. Expected waiting time of a customer in the system, expected waiting time of a customer in the queue, expected number of customers in the system, expected number of customers in the queue. Of course, you can see that the expected number of customers in the queue will always be less than the expected number of customers in the system. Okay, but that's the jargon. Questions? You cannot read something. Which one? This one? Queue. I'm sorry. Okay. Okay. Okay, questions? Okay. Now, another thing that I will do is, okay, so let me erase this part. So I'm going to say that A, this is a parameter, is going to be the number of arrivals per unit of time. And this is called arrival rate. Just as an example, in the barbershop example, the arrival rate of customers was 1.5 customers per hour. So this is going to be the arrival rate definition. And similarly, I am going to have service time or service rate defined. But now I think it's time to relate this A with what we have done in the randomness experiment. Now, think about the following. Okay, let's say that we have flipped some coins, okay? And as a result of coins, what we actually found out was whether a customer arrived or not. Let's say that if we had tails, we say that in that instant, in that time interval, we have a customer coming in. If we had H, heads, let's assume that we didn't have any customer coming in. So for example, here, on the average, I know that we will have 10 customers coming in. So 10 customers coming in is going to be, let's say that A is equal to 10 customers per hour. Okay? So it means that I am going to flip a coin, let's say 20 times for every hour, okay? And find out the actual number of customers that arrived. This is the way that I'm specifying my randomness. So as a result, what can you say about this? Well, you can see that in this specific hour, two groups, let's say that this is not fake but real, okay? 2 out of how many? What is the total here? 3, 8, 17, 20, 25. So 2 out of 25 cases, hours that I did this experiment, I found out that there were only 7 customers that came during the hour. Okay? Now, so 2 out of 25 makes 8 out of 100. So it means that if I convert it to chances of coming, with 0.08 chances out of 1, I will have 7 customers coming in that hour. Now, I can do the same thing for the others. So you can see that what I obtained is, I obtained some kind of a distribution of the number of people who will be able to arrive according to my coin flips. Of course, my coin flips means some kind of a distribution when you add them up. There is a theoretical explanation of that, which we are not going to see. But eventually, what you can see is, you can say that this picture, if I convert it to some values in between 0 and 1, is going to be a good representative of customers coming in several different numbers in an hour. Okay? Now, you can look at this in several different ways, but basically, how we're going to represent randomness is simply, we're going to use some mathematical functions. So one function that we will always use is called okay, so this is actually, we're going to use mathematical functions. So this is, for example, a certain function where t represents the time between 2 consecutive arrivals. And I will explain what it is. So this is time between 2 consecutive, you know what consecutive is, am I right? Following each other. 2 numbers following each other, customer number 1, customer number 2, the time in between those. Consecutive customers. And this is given by a certain function, which is an exponential-like function. So this is a to the power minus at. For t, of course, not for t, positive t values. So if I draw this function, it will be something like this. Okay, please bear with me for a minute because this is an important step to understand the idea of randomness. Okay, so this is how the time between 2 arrivals in my random world that I created is happening. So you can see that this A is actually the arrival rate. Okay? So how is it going to work? This is going to work in a very simple way. Okay? Most of the time, the arrival time will be in this region, but there will be some extremes. Okay? So this is the way to explain it. So this is the arrival time. A is somewhere here. Okay? So most of the time, this is, and the function actually gives the weight of having that kind of an observation. So you can see that the chances, if this is the weight of having this observation, you can see that most of the time, I will have values up to here, because if you add up all this area, this is much larger than the area that we have here. So it means that in most of the cases, I will have an arrival time after the previous one, which is going to be in between these two values. Or it will be most of the time very close to A. But there will be some extremes where it will be 3 hours, 4 hours, 5 hours. The mean is 10 minutes, but it will be 10 hours after I observe another customer. So there is a chance of having very long time between two arrivals. But most of the time, it will be very short. So this is actually the weight. So f of t gives us the weight of a time realized. So, for example, if you look at this figure, this is again the weight of 7 being realized, the weight of 8 being realized, the weight of 9 being realized. Which one is going to happen more frequently in this figure? 10, because the weight is 9 out of 25 compared to all the others. Now, I can have a function like this, or I can have another function. Okay? But basically, the way that we are going to describe randomness is going to be through these type of functions. In queuing theory, we usually use this function, which is called exponential distribution. And it turns out that exponential distribution is very important because it has a very important practical value. It has a tail that can be very long. Okay, what is the meaning of that? It means that in extremes you may have still possibilities. Now, this figure doesn't contain any extremes. We don't even have 13, or we don't even have 14, 15. Okay? Whereas this one has extremes, it means that it might take 2 days until we have the next customer coming in. So our poor barber shop is going to feel very insecure, because with some chances, although very small, we might have that occurring. Okay? In other words, there will be no customers coming in a single day. Very, very little chance. Now, when do you think those chances in real life will happen? Well, when it snows, when people cannot reach that destination, okay, you might have things like this. So if you come to think of it, it's not that extreme in your life. You probably are going, well, we always have 2 or 3 incidents every year, even if it is a very smooth year, because of the snow. So when you look at in the long run, you are going to have these incidences. But of course, the chances are very little. It should snow, and at the same time, it should be something else, and then there would be something else, then you have that problem. So the chances are very small. But still, this is a very good representation in real life, because this is what happens. Murphy's law. Everybody knows Murphy's law. Murphy's law is talking about these type of times. Okay? So if you keep up that time, you're going to have something over there, which means that it occurs actually with some frequency. Okay? So this is the meaning of that. On the other hand, most of our life, maybe 360 days, we're going to have arrivals that are very close to each other. Okay, any questions on this? So this is how we represent. Now, question is here, now I'm going to present you a result of queuing system, a very simple queuing system, and we are going to understand what that result means. Any questions on this? Okay, so now I think it's time to clean this up, unfortunately. Okay, and pose you some results. Now, my plan is the following. I will finish this, and then we're going to take a reasonable break. And then we're going to have a quiz. Most of you guessed that already. And the quiz will be based on the things that I will be doing now. I'm a bad person, I know that. But I was thinking that I will be able to talk about this a little bit earlier. Okay? But I will give you enough time in the break, and then we're going to have a short quiz. Very simple, but short. Okay. So, again, let me give the definitions. Remember, oops. Okay, so let A be the number of arrivals per day. And so what will happen? What is the meaning of 1 divided by A? The best way to understand this is the following. And let's make this hour, actually. It will simplify your understanding. Let's say that we have 2 arrivals per hour. So what is the meaning of 1 over 2? Average time in between 2 arrivals. So this is called the average interarrival. Interarrival means the time between 2 consecutive arrivals. Arrival 1 and arrival 2, the time between is called interarrival time. Okay? And this is called the average interarrival time in units of hours. So these are similar units. Okay? So for example, if I tell you that the average time between 2 arrivals is 30 minutes, and it's exactly the same as saying the average, the number of arrivals per hour, the arrival rate is 2 per hour. It's exactly the same thing, 30 minutes and 2 hours. Now, similar thing can be said for the service time. So I'm going to call H as the service rate, the rate of the server, whether it is ATM or my barber or whoever is serving. And this is defined as the number of customers served per hour. So the explanation will still be the same. So if this is 4, it means that I can serve 4 customers per hour. So what is the meaning of 1 over H? Average time to serve a customer, which will be 15 minutes or 1 over 4 hours. So if H is, for example, 4 per hour, then 1 over H will be the average service time in hours. And in this case, it will be 1 over 4, which means that we're talking about 15 minutes. 1 over 4 hours or 15 minutes per customer. That's called the service rate and service time. Arrival rate and arrival time. Now, these are very important parameters because basically our queuing system is going to rely on those parameters. But as important as those parameters, we also have the distribution of these times or of these times, the inter-arrival time and the service time, what is the distribution of that? In reality, how are we going to obtain the distribution? Okay, flipping a coin is very simple. It's a crude way of doing it. But in reality, we're going to observe the barbershop. We're going to see, for example, observe the barbershop for 3 days. Take a note on the total service time that he or she spends for each customer. You're going to obtain a chart like that after 3 days. So that's going to give you an understanding of the service time of the barber. Similarly, as you are sitting inside, if you don't drink a lot of tea, you will be able to observe the customers coming in. Record the time in the inter-arrival times of those customers. Write that, okay? And at the end of 3 days, if you're not bored to death, okay, you will have a group of statistics that you can use to solve this problem. So we can compute the A and H values using that data, but moreover, we will have an understanding of the distribution that is going to describe the operations of the barbershop. Of course, you can do this for any system that you are observing, as long as you obey the rules of statistical sampling, okay, which you are going to see in the second year. So observing like this is not necessarily a good thing to do. You need to go there at random times in order to make sure that you catch everything correctly, okay? But that is not going to be our job in this course. You're going to learn how to do that in another course. But what I am simply saying is that you can obtain that information. Now, once you obtain that information, now it's time to define certain quantities. Now, the first quantity that I'm going to define will be x. I'm going to define it as x using the notation in the notes that you have. X is called the traffic intensity. And it is defined as A divided by H. So A divided by H. Now, just a little note. At this point, assume that we have a single server. So I am talking about the barber example. I don't want to mix your minds, so think about the simplest possible system. So you have a single server, okay? You don't have more than one person. Okay, and X is defined as traffic intensity A divided by H. Now, what was A? Number of arrivals per hour. What is H? Number of services per hour, service completions, okay? Number of customers served per hour. Now, what do you think this number should be? Should it be a number less than 1, greater than 1? Let us understand what it means when we look at this number. Again, A is number of arrivals per hour, and H is number of service completions per hour. Now, I can simplify this as by saying that you can have 1 over H divided by 1 over A. What is 1 over H? Service time per customer. And this is the time between two customer arrivals, inter-arrival time. Okay. Now, some of you, this kind of a writing will make more sense. For some of you, this will be easier to understand. Okay. Now, let's understand the meaning of this ratio. Now, think about the barber example. What happens if this ratio, x, is greater than 1? So we have 5 customers coming in every hour, but the guy can only serve 2 customers per hour. We're going to have accumulation. So people will start sitting on the pavement outside, waiting to be served. But unfortunately, at the end of the day, even if we don't end the day, the guy continuously works, Okay? People will be accumulating in front of the shop. So we call this the queuing or the waiting line explodes. That's the jargon. So in a reasonable system, we would expect to have servers, adequate servers, to handle the customers arriving. Now, the previous example that I gave is true for Turkcell Turkcell Service Center. Okay, you usually have 99 calls a day, and they can only respond to 3 calls a day. Because sometimes you wait and they will never answer you. Okay? So it resembles that specific case. But as you can see, I would like the reasonable way of thinking is to have this x less than 1. Because if x is less than 1, then I will have enough capacity to handle the arriving customers. Now, this is true on the average. Now, what happens if I include randomness? Now, randomness is going to affect which part of the system more? Think about the previous example that I had for the barber. Now, what will happen if at the end of the day 10 customers arrive at the same time? The barber wants to go home, but 10 customers is lined there. Okay? So you can see that, unfortunately, the barber won't be able to use the idle time that he had in the morning to serve those customers. But that idle time in the morning is included in the average time. So randomness is going to make the server less functional. Because you cannot serve anybody if you don't have any customers. Okay, you cannot put your service in the refrigerator and bring it back when the customer comes. Okay, can you do that? Not in the barber shop. But in a sandwich shop, you can do that. You can prepare the sandwiches ahead of time. That's what they do in, for example, different places in the campus. Because they know that in the lunchtime, everybody is going to come. So they prepare certain sandwiches ahead of time. They have the capability of preparing more, actually. But they do prepare so that they will be able to serve them very quickly. OK. So this is the traffic intensity. And I have 2 more parameters that I'm going to explain. So you can see that the reasonable thing is to have x less than 1. And the meaningless thing is to have x greater than 1 is actually a problem. Okay? Reasonable systems are not going to have x greater than 1. Yes? Okay. Now, that's a technical question that we're going to deal tomorrow and on Friday. But from the way that I explain things, you can see that x is equal to 1 is not going to be sufficient. System will still be exploding when x is equal to 1. OK, so it means that barely making it up is not going to be sufficient. So we cannot tell that to service providers, actually. It's very difficult for people to understand that. Hopefully tomorrow we'll be able to make that up. OK. Now, one formula that I am going to introduce now, OK, I will take, I think, 10 more minutes. OK, then we're going to have a break of 12 minutes, and then we'll have the quiz. OK. Now, at this point, you have to trust me because I'm going to write some formulas down. So those formulas are obtained. Okay, one of the formulas is obtained when the service time and the inter-arrival time both have an exponential structure like that. And hopefully in the 3rd year course, you're going to derive that. OK? So you're going to obtain that formula. The second formula is, regardless of the distribution, it only operates on the means. It is true for every distribution. So we're going to have 2 results. result number 1 is dependent on the distribution. Now, if I define L as the expected waiting time, expected number of customers in the system, and if I define W as the expected waiting time of a customer in the system, my two equations are going to, first of all, give L in terms of X, and the second one will bring L and W together. So the first one is L. The expected number of customers in the system will be X divided by 1 minus X. Or if I replace A and H, this is going to be A divided by H minus A. Okay? It's the same thing. Now let's analyze what this means. I am going to give you a very simple example. Okay? So bear with me for a while. So let's say that A is 1 per hour. This is the arrival rate. H is 2 per hour. So you have to serve faster. We know that. Okay, we have to be faster. So in that case, what will be the value of L? L will be A divided by, and it will be equal to 1. So what does this mean? This means that the average, the expected number of customers in the system at any given time will be 1. So let us see whether it is correct with these numbers. Think about those numbers. So we have 1 person arriving every hour. Okay, and our server capacity is, we can actually clear the customer in half an hour, but every hour we have a customer arriving. So the expected number in the system in general will be 1, which means that we will either have 1 person in the server all the time being served, or in some cases we're going to have people waiting there. So note that if everything was exactly known, what would be the expected number of customers in the system? So let's draw the timeline. If everything is known, so at time 0 a customer will arrive, okay, and in half an hour the customer will be gone. So for the remaining half an hour we're going to have the server idle, and then this is going to repeat itself if everything was based on the averages. So what will be the expected number of customers in the system? It will be 1 for half an hour, 0 for the remaining half an hour. So it will be 1 over 2, actually. But this formula simply tells you that it will be 1. So how did we obtain the remaining 1.5? That's actually the effect of randomness. So that formula, by using this distribution for inter-arrival time and service time, found out that the expected number in the system is more than what we would expect if everything was known exactly, because of this randomness uncertainty that we have in the system. Okay? And so this is how we're going to interpret that. So expected number in the system. Now what happens? Any questions? Okay. Now what happens if x is greater than 1? Look at the formula. What's the meaning of that? Negative. So expected number in the people will be negative. What's the meaning of that? It doesn't have any meaning, because this formula is only true if x is less than 1. Okay? But we know that if x is greater than 1, what is the expected number in the system? Barber shop, think about that. People accumulating in front of the barber endlessly. What will be the expected number at some point in time in 2075? Infinity, practically. Okay? It will be infinity. So I know that it will explode, actually. So this formula is only true if x is strictly less than 1. Now, your technical question, if x is equal to 1, this part goes to 0, actually, and you see that L is infinity again. But we're going to see that tomorrow. OK. So this is formula number 1. Formula number 2. This is, I think, a very useful formula that you're going to see over and over again in the future. OK, it's called the Liddell's law. OK. So this is true. This relation is true regardless of the distributions. And in this, it simply says that W, which is the expected waiting time in the system. Any questions?
A or O?
This is Liddell. Law. Kanun. Liddell's law. Kanun. Law school. We are in the amphitheater of the law school. OK. So here, W is the expected waiting time of a customer in the system. And this is given by L divided by A. So number is related to the waiting time. Let's see that with the example. In the previous example, A was equal to 1 per hour. And L is equal to one person on the average. So W is going to be equal to 1 hour. So this is the expected time that a person waits in the system. Now note that half an hour is the service time. So for half of it, you wait for the service. You are actually being washed and your hair is cut. But the remaining half an hour, you have to read the newspapers that are available there because you wait. OK? So this is how we are going to interpret. Now, this result turns out to be an extremely important result. This is one of the formulas that people ask in the professional industrial engineering exams around the world. We don't have it in Turkey. If you know Liddell's law, you get almost 20% of the passing grade. OK. Now, tomorrow we're going to work on this more. But in the quiz, what I'm going to do is I'm going to give you an example which I want you to read through. You are not going to need your notes because everything is going to be written there. It will be very simple. If you understood what's going on here, you will be able to answer. Any questions? OK, we're going to meet in, OK, just a second. A to K will stay here. The others will go up. V3.